So how do we assess how polar a bond is, or how partially positive and partially negative a covalent bond is between two atoms? That requires us to invoke this concept of electronegativity, which is not really that different from what we've already thought about. Electronegativity, let's jump over here, it's the ability for an atom to attract uh, shared electrons in a covalent bond. So it's really the ability for an atom to want to draw electrons towards itself and become partially negative. So electronegativity then is intimately related to the idea of electron affinity that we'd already talked about. Electron affinity, we said, was if you took an atom and popped an electron onto it, there's some energy associated with that, some net release of energy. Electronegativity, it doesn't quite go as far as adding a full electron, because that would be making the ionic bond, but it's the propensity for that atom to want to draw that electron into itself. And so more electronegative atoms are those that would also really benefit from having an electron added to it. So things that have large negative electron affinities that we talked about before, things like those atoms in the group 7A that are one electron away from being a perfect octet, those things are also going to be coincidentally or non-coincidentally the most electronegative. And so if you look at the sort of figure down below, this is a plot from the textbook that just shows sort of a heat map of electronegativity, and it really mirrors what you would have expected for electron affinity. So electron affinity gives us a true value for the energy released when an electron is added. Electronegativity is sort of just a proxy that tells us generally how willing is that atom to bring an electron closer to itself. And so when we're thinking about the polarity of a bond, a polarity of a bond is really, how polar covalent is it? How ionic is it? Or how different are atoms in electronegativity? So when we think about the polarity of a bond, what we typically do is we actually calculate the difference in electronegativity based on the values that are represented in this periodic table here. These numbers are unitless, and they're computed mostly as a general proxy. They're not true values. They don't refer to any specific energies, but we can get a sense for how polar a bond is based on the difference between those. So, for example, if we wanted to think about how polar is the HF bond, we could look at the difference in electronegativity of the hydrogen atom and the fluorine atom. So that would be looking at hydrogen here and fluorine here. And what we'd see is a 4 minus 2.1, which would give us a 1.9 difference in electronegativity. The general sort of rules, they're not really rules, but they're just sort of rules of thumb for electronegativity, is that more similar electronegativities between atoms, that's going to create a nonpolar type bond, which makes sense, right? If you have two atoms that bond together that have really, really similar electronegativities, then there's really no difference in how those electrons are being pulled or pushed towards another atom. If you have a difference in electronegativity that's less than 2 units, so that's the case for what we have here for HF, then we're going to say that's generally a polar covalent compound. If you have a compound where you're greater than 2 units different, then we're going to call that ionic. these are loose rules of thumb, but they generally give us a sense for how we can look at, is that a really polar compound, or is it a pretty non-polar compound based on just looking at values like this. And so if I were to ask you this, I would never ask you to memorize anything like this. I would just provide you a table like this, and I would ask you to think about the polarity of the bond within the context of these general rules of thumb that I just outlined here. So let's take a minute or two to walk through a couple examples using this notion of the change in electronegativity, or the difference in electronegativity. And let's assign these compounds as whether or not they're polar covalent, ionic, or non-polar covalent. So I would pause the video here, and then when you unpause it, we'll work through those together. Okay, so I just tabulated the electronegativities of each respective atom here. So for this first example, A in purple, this is silicon tetrachloride. That's 4 chlorine atoms that are covalently bound to a central silicon atom here. So what we're being asked to do is assess each one of these bonds, right? How are these bonds? Are they polar or are they non-polar, and where is a partial negative and partial positive lie? So I look up at the table the silicon, so silicon is right here. That's got a value of 1.8, so I put that there. Chlorine's got a value of 3 right there, so I take the difference, and that's 1.2, and it's 1.2 towards chlorine, meaning chlorine has the larger electronegativity, meaning it's going to pull electrons more towards itself. And so we're going to say that the partial negative character is on all of these chlorines, and the silicon then in the center is going to be a little bit more positive. So all of the electron density is being yanked out from the central atom out towards the peripheral chlorine atoms. That's how we should think about this. And because this value is above 0 but less than 2, we're going to call that a polar covalent compound. So it's somewhere in mid-spectrum. Let's look at B. This is cesium bromide. So cesium is all the way over here. That's 0.7. And then bromide's all the way over on the opposite side. That's 2.8. That's got a huge greater than 2 separation in electronegativities. So we'd say that this compound was completely ionic. In other words, the cesium is going to dump that electron over to bromine and make bromide, and those are going to be held together purely electrostatically rather than in a shared covalent way. Let's look at iron bromide, iron 3 bromide. So iron is here, bromine is over here again. So iron's 1.8, bromine's 2.8. That's a difference of 2. So we're going to call these, even though this is a metal and a non-metal, which would make us think that this is generally an ionic compound, it's actually the polarity of the bond is more polar covalent. There is some sharing between them. In fact, this is more of this is less polar of a bond than even the silicon chloride, which would be 2 nonmetals. So these are sort of interesting comparisons here. And then let's do letter D. This is CH4. This is methane gas. So we can look at carbon up here and then hydrogen over here. The difference is going to be 0.4. So we're going to say this is polar covalent. If you were asked to rank the polarity from low to high of each of these bonds, we'd go in and say, well, the carbon-hydrogen bond is the least polar in this compound. So this would be least polar. And then we would have, it looks like, the FeBr bond. That's a little bit more polar. Then we'd have this silicon chloride bond, and then we would have the cesium bromide totally ionic bond out here. That's how we would rank these in terms of polarity. It turns out that the polarity of a bond and the polarity of a molecule dictate a lot of its physical and chemical properties, including its reactivity. And so polarity is a really, really important concept. I should also note that when we're thinking about the polarity of a molecule, we'll talk a little bit more about this later in this chapter. If we've got this molecule that's silicon tetrachloride like this, we just said that each of these bonds by itself is polar, meaning there's a strong draw of electrons out of the silicon and towards the chlorine. But what we can also say is that because these are all pulling in outward and opposite directions of each other, the pull from this chlorine cancels this chlorine, and the pull from this chlorine cancels this chlorine. So the molecule as a whole is a non-polar one. Even though the individual bond is certainly polar, it's pretty significantly polar because it's got this delta of 1.2, it's a symmetric molecule, which means the pull away is equal and opposite, and it makes it nonpolar. If we were to, say, replace this with maybe hydrogen, and so now we've disrupted the symmetry of this molecule, we would say, well, the difference in each of these bonds, the silicon chloride, those are still 1.2 in each, pulling towards the chlorine. With hydrogen, though, we have silicon of 1.8 and hydrogen of 2.1, so there's only actually a 0.3 pull towards the hydrogen, which would mean there'd be a greater distortion of electron density on this side of the molecule compared to this side of the molecule, and we would actually say that this is a polar compound. We'll talk a little bit more about this, but I really want to differentiate between talking about the polarity of an individual bond and the polarity of an entire molecule. And if we're thinking about the polarity of a molecule, we need to add up sort of all of the individual vectors of polarity and see if they are symmetric, canceling each other out, or asymmetric, meaning they lead to a net more negative or positive side of the molecule.